Good afternoon, everyone. My name is Joe Chatelain, and with Jean-Louis Rossi, we came from the University of Corsica to talk about physics, and more precisely about the Balbi model and its developments. So my talk will be split up in two main parts. After a brief introduction, I will present the Balbi model, which is a simplified physical surface fires propagation model. The second part deals with the developments based on the Balbi model we made over the last few years. Corsica is a small island in the Mediterranean Sea, covered up by almost 400,000 hectares of forests and shrubs. It's really a mountain into the sea, so Corsica has always been a burnt territory. Just a few figures: with more than 1,000 hectares burned per year from 2012 to 2016, and more than 8,000 hectares burnt last year. In comparison with fires occurring in the USA, those figures are negligible, but on the Corsican scale they are alarming. The weird thing is that there were no research on fire at the University of Corsica 20 years ago. Professor Jacques-Henri Balbi, 2 times president of the university, decided to create a fire research team in order to give a better understanding of fire phenomena. Its first PhD student, Paul Santoni, which is now the head of our laboratory, worked on a very simple fire model running on very simple geometries. Today, the Forest Fire Research Team is the largest team of our laboratory and is composed of 14 doctors or professors in physics, chemistry, mathematics, or ecology, 2 engineers, and 4 PhD students. In this team, Jean-Louis and I are members of the fire modeling sub-team with, of course, Jacques-Henri Balbi, Thierry Marcelli, and our PhD student, Carmen Awad. Our main goal is to build fire propagation models, but also work on eruptive fires and acceptable safety distances, or use detailed physical propagation models to confront the results to the Balbi model. Let's begin with the Balbi model from its origins to the present day. So, 20 years ago, the main part of fire propagation models was split up in empirical models, for instance the well-known Rothermel model, and detailed physical models, the so-called multiphasic models, integrated into simulators such as Firestar, FireTech, or WFDS. Simplified physical models were yet another type of model, for instance Piney, Peterson and Koo, which were physics-oriented enough with a computational time close to 0. At that time, at the University of Corsica, we have neither fire laboratory nor supercomputer, so we could neither carry out fire experiments nor use detailed physical models. The only things we had were pen, paper, laptop, and of course our brain. Our goal was to build a simplified surface fire propagation model, no crown fire model, that could be used by people involved in firefighting or in fire management. So this model had to be physics-oriented, 3-dimensional, faster than real-time, and provide a good accuracy. The use of simplified physical laws had to give the main physical characteristics of a fire front: rate of spread, flame tilt angle, flame temperature, etc., as a function of the wind speed, the terrain slope angle, the fuel moisture content, and other fuel characteristics. The model was built in 5 steps, from a simple model to a complete model working at the field scale. This simplified propagation model has to give the main physical characteristics of the fire front. So rate of spread, flame tilt angle, flame temperature computed at mid-height flame, flame height and flame length, fire front depth or fire front width have to be easily computed. The point is how to obtain a simplified physical model. The important thing is to avoid partial differential equations, which need strong assumptions on the gas phase. Then we have to consider average values of the variables, for instance the mean flame temperature. And third, we have to consider simplified physical laws, for instance a simplified mass or energy or preheating balance. Finally, the rate of spread appears to be the solution of an algebraic equation. The first operational model took into account three energy transfer modes. The flame base radiation, I mean the radiation from the fuel burning particles area. The burning fuel unburnt fuel interface is assumed to be a black radiant panel, and we use a usual Stefan Boltzmann modeling. Flame radiation with the flame as a gray radiant panel. And a convective cooling in front of the flame. This cooling leads to a strong assumption. The flame radiation only impinges the unburned fuel under the flame. A simplified preheating balance gives the expression of the rate of spread as the sum of the two previous contributions, and a velocity composition law provides the definition of the flame tilt angle, which depends on the terrain slope angle, the normal component of the wind velocity, and the upward gas velocity. This model was confronted to later experiments with success, but some weaknesses remain. Some equations of the model come from empirical laws. For instance, the flame height is computed with the McCaffrey correlation. Another weakness lies in the definition of flame radiation. And last but not least, the simplified model has three model parameters. Obviously, it needs to be improved. 3 years later, three improvements were made. First, we changed the McCaffrey correlation for a physical law obtained with a simplified vertical momentum balance. We also came up with a better modeling for the radiative fraction, and we introduced a fresh cooling which models the backfire better. This improved model was confronted to a set of laboratory experiments with strong winds and non-parallel wind and slope. This version of the propagation model was integrated into the 4-fire simulator, which is now coupled to the MESO-NH atmosphere model. However, this model still neglects convection and then poorly represents laboratory experiments with well-ordered, vertically oriented fuel bed. The next step is about the development of a convective model. The point is to determine what convection we are talking about. When we talk about convection, we mean the flow of the hot gases. So as to check the validity of a convective model, this model has to be confronted to experiments with well-ordered and vertically oriented fuel beds. Indeed, many authors from Wolf, Carrier, and Fendel to Mark Finney proved that convection is the dominant heat transfer mode in this type of experiments. So, with those specific fuel beds, radiation from the flame base is still considered, but is expected to be not very important because of the well-ordered fuel particles. Flame radiation only impinges a very small surface of the fuel bed because of the verticality of fuel particles, and then will be neglected. As several authors did, we consider that the flame is quasi-laminar in its first half above the vegetal stratum, and then it acts as a barrier to the airflow. So we take into account the flow inside the flame base. a gas particle inside the flame base is subjected to wind speed and upward gas velocity. Some gas particles go out of the flame base through its top and then go into the flame. But some gas particles go out of the flame base through the burning-unburnt fuel interface. This hot gas flow creates a contact flame which ignites the unburnt fuel. I think everyone has recognized the fingers of fire observed by Rothermel and Anderson. We have confronted the convective model to 172 laboratory fires picked up in the literature. We can observe the good agreement between predicted and observed rate of spread with a very small normalized mean square error, a fractional bias close to zero, and the Pearson's correlation coefficient close to unity. But the most important thing is that the model has no model parameters. The only changing characteristics from one experiment to another are wind velocity, terrain slope angle, and fuel characteristics. As we have a radiative model and a convective model, we combined them to obtain a complete model. Note that the radiative model was improved with the removal of all the model parameters. One example is the radiant coefficient. 10 years ago, it was a fitted coefficient. Then we produced a physical modeling of this coefficient with a model parameter, which finally disappeared. Okay, now we have a complete model with radiation and convection, but what is the dominant heat transfer mode? In fact, the rate of spread is an increasing function of the wind velocity. After a fast increase, the rate of spread reaches a plateau, which is obtained for a threshold value of the wind speed. Below this value, we can say that flame radiation is negligible. Above this value, the competition between flame radiation and convection involves a negligible flame-based radiation. This model was confronted to the 357 laboratory fires carried out by Catchpole et al. We can observe a small error, less than 8%, a light underestimation, and a Pearson's correlation coefficient close to unity. Those experiments are very important because Catchpole and her co-authors gave all the fuel characteristics needed by our model. This year, we confronted our model to the field scale, and we observed pretty poor results at the field scale. The question is why? In fact, in the laboratory model, we considered that all the convection was absorbed by the unburnt fuel. There were no losses. In the field, we made a new assumption. We consider that one part of the convective effects is absorbed by the ground. So convection will be changed in this case, but the additional term could also be used at the laboratory scale, so we only have one model. This field scale model was confronted to almost 200 fires, mainly shrubland and grassland fires, and the results are encouraging with an error around the 20% level and a good correlation. This year, we also confronted the field model to laboratory experiments in order to check the validity of flame height and flame length submodel. We confronted the model to almost 100 laboratory fires, and we can observe a very good agreement for the rate of spread, which is not a surprise. But we can also observe a good agreement between predicted and experimental flame height or flame length. This confrontation was necessary because Jacques-Henri Balbi developed the flame height submodel 10 years ago, but never checked its validity. In short, we can say that 20 years ago we started with a simplified semi-physical surface fire propagation model with many weaknesses, and we finished with a simplified physical model which takes into account radiation and convection, and above all without any model parameters. The radiant coefficient is an example of this work. from a fitted parameter, it gained a physical meaning. Obviously, taking convection into account and the removal of all the model parameters, thanks to physical modeling, are the two major improvements. We confronted the model to several fires with an average error of 8% at the laboratory scale and about 20% at the field scale. The second part of the talk is about the developments of the Balbi model, and first we are going to deal with marginal burning. When we talk about marginal burning, we mean propagation or non-propagation under no wind and no slope conditions. So the mainspring of the spread is the flame-based radiation. Our main goal in this work was to find physical values of non-propagation criteria. The first criterion deals with the leaf area index and is due to the expression of the rate of spread. Indeed, we can observe that in order to obtain a fire spread, this term couldn't be a negative term. So, a bounded LAI is a no-go criterion. The second criterion depends on the fuel moisture content. In order to propagate, the flame-based depth must be greater than the optical depth, which means, after some calculus, that a fire will not spread if the fuel moisture content is greater than a threshold value. This year, we started another collaboration with Dominique Morvan from Marseille about a PhD student which investigates the influence of the fuel moisture content on fire spread with the CFD software Firestar developed by Dominique. For the moment, we only consider no wind or weak wind velocities and no slope conditions. But the goal of this PhD is also to investigate the role of fuel thickness and the role of wind on the non-propagation. We finally confront the numerical results obtained with Firestar to analytical relationships obtained thanks to the Balbi model and empirical relationships found in the literature. But this work is still in progress. The second and very important development concerns eruptive fires. Let's talk about one example of extreme fire behavior, I mean eruptive fires. Eruptive fires are characterized by a sudden and unpredictable acceleration of the rate of spread, even under low wind speeds or small slope angle conditions. So, eruptive fires are extremely dangerous for firefighters, and they are the cause of several human losses. This list is not an exhaustive list, but we can observe that the major part of eruptive fire accident takes place in the USA and in the Mediterranean basin. As I previously said, Corsica is a small territory in the Mediterranean Sea, but in 2000, 2 firefighters died in Palaska. It's a small village on the western coast of the island. This is maybe the only filmed eruptive fire. Here is the 2 minutes movie. I'm sorry because it's not a high resolution movie. It was filmed with a cell phone, not a smartphone. Please have in mind that we are in 2000. So it was filmed with a cell phone by a tourist from the road. We can observe a fire spread in a small canyon. The wind speed was not important, but at the end, the whole left side of the canyon was ignited in less than 1 minute. And 2 firefighters, which were located on the ridge far from the fire, were completely surrounded by the flames and unfortunately died. Now we can see the beginning of the fire eruption. can guess a very fast fire spread. And now we can see the left side of the canyon, which is completely ignited. So, if one can find in the literature some empirical models which describe the fire behavior during the eruption, Viegas or Dold for instance, to our knowledge, none of them are able to predict the eruption's onset. Some models follow from several explanations of the phenomenon: gas accumulation, flow attachment, convective flow induced by the fire. So the main question is about the explanation of the phenomenon. Among several explanations found in the literature at the University of Corsica, we considered the pioneering interpretation proposed by Viegas because it has never been refuted by an example of eruptive fire accident. It consists in a feedback effect caused by the convective flow induced by the fire to compensate for the draft caused by the hot gases moving upwards. This induced wind was proved with laboratory experiments by Viegas and Pita. It was observed at the field scale in the Gestosa fire experiments and also measured in the Fresho accident. Viegas and Pita created a canyon geometry on a burning table where fire was ignited at the base of the canyon. In order to investigate the role of induced wind, an experiment was carried out in which induced wind was inhibited by a plate placed across the base of the canyon. Practically at the same time after ignition, the difference of fire behavior is really clear. At the field scale, the effect of induced wind was observed in one plot of the Gestosa fire experiments. As we can see on the picture, the two sides of a mountain were split up in a huge set of plots in order to make field experiments. One plot has a canyon geometry and several gusts of about 100 kilometers per hour were measured only at this canyon plot. But induced wind was also measured during the Fresho accident in the north of Portugal, near the Spanish border. The fire ignition was located at the north of Fresho de Espada Cinta. The wind was slightly blowing from the northwest, and the fire was given as extinguished at this point, except a small section of the 50 meters fire front width. But this point is the base of a canyon, and the fire erupted, causing, unfortunately, the death of 2 people. At the top of the ridge, there was a meteorological station which recorded, among other parameters, the wind direction and velocity. The interesting thing is that wind changed its direction from approximately downslope to upslope, and its velocity increased from about 12 to 64 kilometers per hour, with gusts at 96 kilometers per hour, without any other atmospheric phenomenon. In our opinion, this is a clear proof of the role of induced wind in the eruption's onset. Thanks to a simplified mass balance, a physical modeling of the convective induced wind is coupled to the radiative Balbi model. Note that we are interested in the fire front behavior, not in the backfire, but we do not consider a fire which spreads with the same depth. We are interested in the increase of fire front depth with induced wind. This coupling gives an analytical condition of safety. As long as this relationship is satisfied, a fire cannot erupt. But this won't be the case with a light fuel, I mean with small density and specific heat, with a weak ligneous component, because it plays a role in the heat of combustion of the pyrolysis gases, and due to our modeling in the flame temperature, a sufficient fuel load, which plays a part in the absorption coefficient, and a dry fuel thanks to the fuel moisture content. We also need dry summer conditions and or a large fire front, because the fire front width plays a part in the coefficient Y. When this relationship is no longer satisfied, eruption is possible, but it is not sure. Then it depends on the value of the terrain slope angle. Unfortunately, it is not possible to find an analytical condition which gives the threshold value from which eruption is sure. We have to solve the model numerically. First, we confronted the model to laboratory experiments. The first set of experiments was carried out on an open inclination table. The fuel bed used was straw, and 4 experiments with different values of the slope angle led to no eruption observed. Our model gives exactly the same results. The second set of experiments was carried out on an inclination table with lateral walls. These pictures describe the fire a few seconds after ignition. 10 seconds later, if the spread seems usual for the slopes up to 25 degrees, the fire erupts for the 2 last values of the slope angle. So the threshold value of the slope angle is between 25 and 30 degrees. Our model shows the eruption for an 26 degrees slope angle, which seems relevant according to the experiments. The model is finally confronted to an accident that happened 11 years ago on the Kornati Islands in Croatia. The ignition point was located near the Vrulje Bay. The fire was pushed by the Yugo, and the fire spreads to the northwest. Up to this point, Sipnate Canyon, whose average slope is about 9 degrees. The fuel bed was grass. The flame length was not important. A large fire front came to this canyon and fire erupted, causing, unfortunately, the death of 12 firefighters, one being badly injured. With these parameters, our model gives a fire eruption for an 8 degrees slope angle, which matches the real conditions. All the previous results have been obtained thanks to the radiative-only Balbi model. This model has 2 main shortcomings: the presence of 3 model parameters and the lack of convection. This year, we completed the development of a new radiative-convective surface fire propagation model with no model parameters and a new term which expresses the convective effects. The induced wind modeling gives an equation for the rate of spread as a linear function of the wind speed, and contrary to the first model, the combination of the 2 expressions of the rate of spread leads to obtain an analytical value for the threshold slope angle from which eruption is sure. This expression depends on several fuel characteristics and on fire dynamics properties. The model was confronted to the set of experiments performed by Liu et al. Liu evaluates the effect of slope on spread of a linear flame front over a pine needles fuel bed. The slope angle varies from 0 to 32 degrees. The results on the rate of spread are the following, which gives the trend of the rate of spread with a very small increase up to 25 degrees, and then a very fast increase, practically an exponential increase up to 32 degrees. We can assume that the threshold slope angle is between 25 and 30 degrees. Our analytical value of the threshold slope angle is 28 degrees, which seems relevant according to the experiments. As a conclusion, we can say that according to our model, all the situations favorable to a fire eruption are those in which the fire front width remains important. Obviously, canyons have very dangerous geometries. The Famalicão accident or the laboratory experiments conducted by Viegas and Pita are other examples. Finally, as it was proved by Sharples and Dold, trenches or corridors are very dangerous situations. So, we have a steady-state propagation model only designed to predict the eruption's onset. If we want to know the fire behavior during the eruption, we have to use the unsteady version of the propagation model, because a fire eruption is obviously an unsteady phenomenon. We can find the threshold slope angle from which eruption will occur, but in fact, thanks to a very fast code, we are able to find the value of any of the parameters involved in the model which can cause an eruption. We are not able to take into account a heterogeneous vegetation, but this limitation can be solved using an equivalent fuel model. And we are not able to take into account eruptive crown fires because the propagation model is only designed for surface fires. Now, I'm going to talk about a multidisciplinary work involving researchers in computer science, in physics and mathematics in order to propose a simple tool that foresees safety zone sizes at the field scale. Wildland fires represent a growing threat on human infrastructure and activities, particularly due to the spreading of the wildland-urban interface. From a fire safety point of view, the fire has two main impacts. It can damage structures and affect people. Particularly, firefighters wearing protective equipment have to remain at a close distance from the fire front to fight against it, and not too close in order to keep safe. In this part, I'm going to present an application that determines safety zone sizes at the field scale as a function of fire environment and fuel characteristics. Safety zones are man-made landscaped areas without vegetation that act as barriers to stop or slow down a fire spread, as fuel breaks do. Here we have one example in the USA and another one in Corsica. In Corsica, a width of 100 meters is settled on the basis of the expert's judgment, wherever the safety zone location, without any scientific study. But safety zones are also designed for providing firefighters access and to which the men and their equipment can retreat to escape injury. This is the main difference between safety zones and fuel breaks. In the latter case, a correct sizing of safety zone width and then a correct computation of safety distances is crucial in order to keep the firefighters safe. The acceptable safety distance is defined as the distance between the fire and firefighters required to prevent them from injuries. The distance is usually set thanks to a general rule of thumb given by Butler and Cohen. It should be at least 4 times the maximum flame length. A common assumption consists in correlating fireland intensity with flame length, but these empirical relationships cannot be used to compare fires in fuel types. At the University of Corsica, we preferred a simplified physical approach, which consists in coupling our physical propagation model with a flame length submodel and an operational relationship for the safety distance. First, we need to know the fuel characteristics, which are input data of the Balbi model. The model outputs are the main physical characteristics of the fire front, including the flame temperature. These outputs are necessary to compute the flame length. Finally, flame length and fire front characteristics are inserted into the analytical relationship, which allows the calculation of acceptable safety distance. Okay, this formula developed by Jean-Louis is a big formula, but there is one important thing in this big formula. The model takes into account the threshold heat flux level, which I'm going to talk about in the next slide. So, at the end of the process, the ASD is computed. If we list advantages and disadvantages of each method, we can say that the empirical approach is very simple to use because of its formula. The fire characteristics are not necessary because we usually have ranges for the maximum values of fire line intensity according to the fuel, and it is easy to estimate the flame length and then the ASD. The first shortcoming concerns the rule of thumb which has been established on the flat ground and is used with the same formula on sloped terrains. It has also been established for a heat flux level which corresponds to the maximum tolerable value for firefighters. So it is not possible to change the type of target, people, exposure, or buildings, for instance. Another shortcoming concerns the several correlations found in the literature for the same fuel type in case of different experimental conditions. The advantages of the physical approach are numerous. It represents a closed model which can be applied to any fuel and also to any heat flux level. Moreover, its quickness allows an implementation on various supports such as smartphones or tablet devices, for instance. But in order to run the model, we need all the fuel characteristics and accurate propagation and flame length models. So, in order to formalize our physical models, we collaborated with the computer science team of the university. The main goal was to propose an online computational framework and to develop a mobile application to visualize the setting up of safety zones on the field. We use the discrete event system specification formalism introduced by Ziegler about 20 years ago, which is an abstract formalism for discrete event modeling. The DEVS formalism is used as computational tool, and we integrate physical models in a DEVS-based simulation framework. The software architecture begins with the end user. When the user launches the application on its tablet device, he has to define the path of the safety zone, either manually or automatically if he is moving on the field. Once the coordinates defining the path are recorded, these data are sent to our web service hosting the DEVS framework. Before launching the computation, the web service fetches topographical and meteorological data for each point. Now, the web service can compute the ASD. And finally, the results are sent back to the client for displaying. The graphical user interface is very important for the end user. Corsican firefighters want it to be as simple as possible with a few options at the start. So the screen is entirely covered up by the world map. The changes in the options are possible thanks to a menu that displays and hides automatically on the left side of the GUI. For the moment, it is possible to choose the vegetation type and other options as fuel height, for instance. It will also be possible to switch to the empirical relationship provided by Butler and Cohen. The application has two different possibilities for the definition of the path. The first one consists in manually setting the points on the map. We just have to touch the screen to place each point of the path. The second one is useful on the field. The GPS locates the user position and automatically records the path. Here is an example of the running application. First, we zoom in on the map to choose the safety zone location. Then we set the path. As we can see here, the path is set manually. We choose the vegetation type and the fuel height. We click on the Calculate button and the safety zone dimensions are estimated and displayed on the map. Note that the time to display the results is the real time with a Wi-Fi connection. I mean that we didn't edit the movie clip. 2 years later, people involved in fire management preferred to give up iPads and to have a tool on their personal computer. So we developed a web interface for DIMSAL. The GUI is like the iPad one, with the map on the major part of the window and a menu on the left. We still have to set the path and the vegetation type. Then the software computes numerous simulations, and it is possible to visualize all the results on the map. In this example, we just decided to visualize the simulations computed with the Butler's empirical rules. In short, we can say that we have a prototype of application which estimates ASD and therefore safety zone width. The application's kernel is physics-based for the propagation model, the flame length model, and the ASD model. It shows that the DEV's formalism can be used as a computational tool because DEV's combines the advantages of a simulation-based approach with the rigor of a formal methodology. It is also user-friendly with a very simple graphical user interface. So we provide to firefighters a decision-making tool which will check if the dimensions of the existing safety zones are valid. This prototype will be tested by Butler for the USDA as soon as the issues with the Google Maps API will be settled. In the next future, our collaboration with Corsican firefighters will allow us to adapt the application to assess ASD for buildings. It's time to conclude. So as a conclusion, we can say that the simplified physical propagation model developed by Jacques-Henri Balbi has become a physical fire behavior model. Indeed, it was the core of several additional works as the definition of non-propagation criteria, anticipation of fire eruptions triggering, and the determination of safety zones width. Now, a lot of works have to be completed. Improve the model thanks to a confrontation to a huge set of field experiments. Another important work concerns the mass loss rate in order to change the Stefan Boltzmann modeling by a new modeling of flame emissivity. Firefighters also wait for an operational tool on iPad or personal computer which allows to foresee a fire eruption. And finally, we plan to adapt the DIMSAL software to assess ASD for buildings and then change DIMSAL in a wildland urban interface software. Thank you for your attention.